In this lesson, you'll learn to prove triangles are similar. The objective is to use three postulates and theorems. One is angle-angle, the other is side-angle-side, and the other is side-side-side similarity postulates and theorems. It's very much like the congruent postulates and theorems that we've learned, but these are for similarity. And you're also going to learn how to use similarity to find indirect measurements. The first postulate is the angle-angle similarity postulate. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. So in this particular example, we have angle S is congruent to angle M, and then we have angle R is congruent to angle L in the second triangle. So that means that triangle SRT is similar to triangle MLP. The next is the side-angle-side similarity theorem. And it states that if an angle of one triangle is congruent to an angle of a second triangle, and the sides that include the two angles are proportional, then those triangles are similar. So here we have, if our sides are proportional, so if AB over QR is equal to AC over QS. So you've got proportional sides between the two that are marked in red in this diagram. And we have angle A that's congruent to angle Q. So you have the angles that are congruent between the sides that are proportional. AB over QR is proportional and AC over QS is proportional. Then you have triangle ABC is similar to triangle QRS by side-angle-side similarity. The third theorem that we have here is the side-side-side similarity theorem. So if we have corresponding sides of two triangles are proportional, then the triangles are going to be similar. So here the corresponding sides are AB and QR. So put that as a ratio equal to AC over QS are corresponding sides. So that's the second ratio, and that's equal to the third ratio of sides, which is BC over RS. So if that's true, then we can say that triangle ABC is similar to triangle QRS by side-side-side similarity. The last thing in this lesson is about indirect measurement. Indirect measurement. So an indirect measurement can be used to find lengths that are difficult to measure directly. And we'll use something called an angle of reflection to work this type of problem. So one method of indirect measurement uses the fact that light reflects off a mirror at the same angle at which it hits the mirror. So the last problem will work. It's going to use indirect measurement and the angle of reflection. You'll see how that works. Let's go over to problem 1 and look at using these postulates and theorems for similarity. In problem 1, it asked, are the two triangles similar, and how do you know? So you're going to use one of the postulates and theorems, these 3 that we have in this lesson, for similarity. In A, you have triangle RST and triangle NOP. And because of the markings in the diagram, we have angle R is congruent to angle N, and we have right angles at S and O. And we know from the right angle congruence theorem that all right angles are congruent. So we have 2 corresponding congruent angles. So we can conclude that yes, these are similar by angle-angle similarity. On the B part, we have triangle GHT with angles G is 40 and T is 80. And we have triangle DEF. Angle E is 45 and D is 40. So right off we can see that we have 2 40-degree angles that are congruent in angle G and D. But we have to determine if we have one other angle that's congruent or not. We don't have any sides, so the only thing we could try to use is angle-angle similarity. So we need to find the measure of the third angle in each one of these triangles. So we're going to use the triangle angle sum theorem. So 40 plus 80 is 120, and 180 minus 120 is 60. So angle H is 60. In the bottom triangle, we have 45 and 40, which is 85. So 180 minus 85 is going to be 75. So that angle F is 75. So we don't have a second angle that's corresponding and congruent. So these are not similar. Scroll down to problem number 2. In problem 2, we have a set of triangles in part A, and it asked, are the triangles similar, and if so, write a similarity statement. So it gives us lengths of sides. We don't know anything about angles, so we're going to try to use side-side-side similarity to see if all 3 sides are proportional, to see if they are similar or not. So to do this, how do you match up the sides? You go with the smallest side over the smallest side of the second triangle. So if we look at triangle DPL, the smaller one up top, the smallest side is 5. So we're going to put that over the smallest side in triangle SKR, which is the 10. So those are the corresponding sides, and we're going to see if that is equal or not. We don't know yet. Is that equal to, let's look at the second longest length, or the middle length of the first one is 12. And then let's look at the middle, or the second longest length in the second triangle, which is 24. And we have to see the third sides. Is that going to be equal to the proportion of the third sides, which is going to be the longest side in DPL is 13, and the longest side in SKR is 26. So we can see pretty easily by reducing these fractions that 1/2 is equal to 1/2 is equal to 1/2. So they are proportional. And so they are similar by side-side-side. So we have side-side-side similarity, and we write a similarity statement. Triangle DPL is similar to triangle SKR. In the second set of triangles, in B, we have a triangle within a triangle. So anytime you have a triangle inside of a triangle, you're going to have usually a part that's shared between the two. So here we have triangle STU, which is the smaller triangle on the inside. And then we have the larger triangle. The larger triangle that's on the outside is our TV. So you can see the two triangles. And you see that they share an angle. Both of them have angle T that they share. So that's going to be a shared angle that's congruent between the two. So let's look at the sides that are on each side of that angle to see if they are proportional or not, and we might be able to use side angle side with this. So let's look at the sides. We have ST. We have ST in the smaller triangle, and that corresponds to RT in the larger triangle. And we need to see, is that proportional? Is it equal to the UT in the smaller triangle over side VT in the larger triangle? So if we substitute the numbers into this, we're going to have ST is 10 and RT is 10 plus 4, which is 14. Is that equal to UT is 12, VT is 12 plus 4.8, which is 16.8. Now it's kind of hard to see because that's not easy to reduce these fractions. If you ever get to that point where it's difficult to see as fractions, are they congruent or not, then just put it in your calculator and convert them to decimals and see if they are equivalent decimals. So 12 divided by 14 is 0.714286. And that is equal to, if I put in your calculator, 12 divided by 16.8 is also 0.714286. So they are equivalent fractions because they're equivalent decimals. So we have proportional sides. You have angle T is congruent to angle T because of reflexive property. That's the angle in between the proportional sides. So we have the triangles are congruent. Triangle STU is congruent to triangle RTV by side angle side similarity. Let's go down to problem 3. Once again, proving two triangles are similar. So in this problem, we're giving that angle S is, measure of angle S is 35. The measure of angle LTC is 55. And you have right angles at angle STL and angle TLC. And all that is marked in the diagram. So using this, we need to see and write a proof that proves that triangle STL is similar to triangle CLT. So, first statement is all of your given information. So all of your given information would be your first statement. And then let's find the measure of angle C and see if it is equal or not to the measure of angle S. So measure of angle C is going to be 180 minus the 90 degree angle and then minus the 55 degree angle. So it is equal to 35 degrees. So, and that's using the triangle sum theorem. So then we can state that the two right angles are congruent. We have angle STL is congruent to angle TLC because of right angle congruence theorem. And so now we can state that triangle STL is similar to triangle CLT because we have two angles that are corresponding and congruent between the two triangles, and that's angle-angle similarity. In the last problem, we're finding lengths in similar triangles, and this is where we're going to use that indirect measurement and angles of reflection in this problem. It says Benjamin places a mirror 40 feet from the base of an oak tree. When he stands at a distance of 5 feet from the mirror, he can see the top of the tree and the reflection. If Benjamin is 5 feet 8 inches tall, then what is the height of the tree? You need to draw a picture for this to see this. So, once again, he's placing a mirror 40 feet away from a tree. So we're going to draw a little tree. There's our tree. And he's placing a mirror. It's going to be 40 feet away from the tree. So here's where his mirror is. 40 feet away from the tree. And then he's standing 5 feet away from the mirror. So let's go 5 feet away from the mirror. And let's draw Benjamin. Okay. Now he is 5 feet 8 inches tall. Let me find a different color. He is, his height is 5 feet 8 inches. And so the question is, how tall is the tree? So that's what your X is the height of the tree. So what you need to do is make similar triangles out of this. So if we go from Benjamin to the mirror, and then from the mirror up to the top of the tree, these angles down here at the mirror, those are the angles of reflection, and they are congruent angles. Now the angle over by Benjamin at the ground is a right angle, and the angle over by the tree and the ground is a right angle. So we have similar triangles by the angle-angle similarity postulate. And we can use this to set up a proportion to solve for the height of the tree. Now one of the first things you have to do to set this up is you need to convert 5 feet 8 inches to a decimal. So if you just take 8 divided by 12, because there's 12 inches in a foot, that's going to give you the decimal equivalent of 8 inches. And that's going to end up being 5.67. That's 5 foot 8 inches. So the height of Benjamin over the height of the tree has got to equal Benjamin's distance away from the mirror is 5 feet, and the distance of the mirror from the tree is 40 feet. So that is the proportion that you've got to set up and solve. So you cross multiply these, and you're going to get, let's reduce this first. That'll make it easier. Because 5 will go into 5 one time, and 5 will go in there 8 times. And that'll make it a little easier when we're cross multiplying. Because then when we cross multiply, you're going to get x is equal to 45.36 feet. Now, if you want to go through converting 45.36 feet, the 36 feet part back into feet and inches, because you've got 45 feet there, and the 36 hundredths of a foot, how do you convert that? Well, to do that, you need to use another proportion, which is just, if you do 36 hundredths, 36 over 100 is equal to x over 12, and solve that for x. That's going to get that decimal of 36 hundredths back into inches. So if you solve that, x is going to be 4.32 inches. So your answer for the height of the tree is going to be 45 feet and 4 inches.